Hey gang, you guys hear me today? All right, let's try to make sure I get this right. Who's got the giant bear as their Thomas? Where does that bear live?
It is the picture taken in Yosemite.
Oh, in Yosemite. Oh, cool. Okay, cool. Yeah, I guess I don't have a little picture that takes my place when I'm not here. I have to get that. Alrighty. Hey, some of you guys, when you tried to log in today, it told you that you were in a waiting room, I guess, and you had to wait for me to admit you. Is that true? They told me that that's how it was going to.
They just told me that you had to start it, not that you had to admit us.
So Jacob, when you did it, as soon as I started the meeting, it just went on for you?
I think that's what it said for me. It says host had to start the meeting, and then it brought me to this.
Okay. Was anybody else told that they were in a waiting room or something, that I had to admit you? Because the reason I ask is somebody, and I don't know whether it was the math department or the university-wide IT, but one of their attempts to reduce this thing called Zoom bombing is they set it up so that the default now is that every meeting will start with a waiting room, and that the students can't get in until I check to see who they are, and then I can admit them. Well, I don't really anticipate a problem, so as soon as the meeting starts, then I can set it so that everybody gets in as soon as you think you've logged in. But I'm noticing that some people seem to be forced to go into a waiting room and other people are not, and I don't understand the difference. So anyway, if you notice that you're in a waiting room when you're either coming to the class or you're trying to visit me in office hours, just be patient, because I think I will notice at some point that somebody is waiting to get in, and I'll change it so that everybody's admitted. Oh yeah, Andrew, you said that you were in a waiting room. The waiting room thing only happened if the person isn't logged in with their UTE ID. Ah, that's interesting. Yeah, you guys are supposed to be, I don't know. The system was designed to make every person with a UTE ID get admitted automatically. And I thought everybody who didn't use that was just completely rejected from the Zoom meetings, but apparently you can get into a waiting room. I don't know. I apologize. They keep changing the technology on me. I'm trying to get used to it. Anyway, I sent you guys an email, I guess it was this morning, bringing you up to date on a few things that came up in the discussions on Monday. Did you guys have any questions about anything that was in there, or any new problems that have arisen? Anything that you need me to address? All right. Well, then we can get right into some number theory. So I wanted to take advantage of the Fermat theorems that we were talking about last time, and another one due to Wilson. So let's see if we can get those into class today. Turn this around. There we go. I'm very proud of my little camera arrangement here. I was telling my vector calculus students how this is an example of a high-dimensional setting, a high-dimensional object, because it has like 6 degrees of freedom for how it can move. And so every positioning of the camera is actually taking us to a different point in a 6-dimensional space. But anyway, it lets me use it as a document camera as well as face-to-face. All right, so let me remind you again of the variations of Fermat's theorem that we discussed. So the first stage was to prove that if p is prime and n is any integer, then n to the p is congruent to n modulo p. Then a small variant of this comes from multiplying both sides by an inverse to n mod p, which does exist as long as n is co-prime to p. So I have to put that in as an extra condition now. If p is prime and p does not divide n, then the conclusion is that n to the p minus 1 is congruent to 1 modulo p. And each one of these has a contrapositive that I used last time to discuss primality testing. So I'll state it this way: if n is an integer and n to the p power is not congruent to n mod p, then p is not prime. And then unfortunately, the converse of this one isn't true. It feels like it should be true, but it isn't, unfortunately. You would like to be able to say, hey, I have a number p that I think is prime, and so I'm just going to grab any other integer n and raise it to the pth power and see whether I get n, I mean something congruent to n at the end. If I don't, then I know that p is not prime. And if I do, well, then there's no conclusion here. So this does not say, that we do not have the converse of this one. We do not know that if n to the p is congruent to n, that does not necessarily mean that p is prime. For starters, what if n was equal to 1? 1 to the pth power is congruent to 1. Doesn't matter what p is. Obviously, that's not true only for primes p. So a statement like this can be true even if p is a composite number, but it might be true for some n's and then not for other n's. And so there are some interesting examples that that are worth trying. For example, if n is equal to 2 and p is equal to 341, I think I had this example last time. If you compute n to the pth power, you do, in fact, get 2 modulo 341. But on the other hand, the number 341 is not prime because it's actually equal to 31 times 11. And even if you weren't able to find this factorization, you could still check that the number 341 is not prime by trying n equals 3. But if n is equal to 3, then n to the 341st power is, in fact, not congruent to n modulo 341. So obviously, we know that the number 341 is not prime because we can factor it, but it doesn't even work. The number 341 doesn't even try very hard to masquerade as a prime because, well, using the n equals 2, or as I said, n equals 1, would make this statement be true. But as soon as we get to n equals 3, already that statement is not true. But I would like to introduce you to another number, which works a little harder at masquerading the fact that it's actually a composite. So here's a theorem. If n is a number that's co-prime to 561, then n to the 561st power is congruent to n modulo 561. In other words, for every integer n, well, as long as it's not actually divisible by any, it doesn't share any prime factors with 561, and for every integer, you still manage to have something like the Fermat theorem be true. And yet, let me put this in as a little remark, the number 561 is not prime. 561, it can be written as 11 times 51, but 51 in turn is 3 times 17. So obviously the number 561 is not prime. Nonetheless, this is an interesting theorem to prove because it lets us take advantage of exactly the Fermat theorem that we're discussing. So let's have a proof of this. Oh, Jacob, you have your hand up. Sorry, I didn't check.
Is this the only number that it happens with, or are there other numbers that are?
That's a good question. And the answer is no, 561 is not unique. 561 is the smallest example of this. The statement that, if I can replace this 561 here with C, then this property is the definition of what it takes for C to be a Carmichael number. C is so Carmichael was the name of a early 20th century mathematician. Carmichael number. And so the theorem is that 561 is an example of a Carmichael number. It happens to be the smallest Carmichael number. But then, of course, you are asking whether or not it's the only Carmichael number, and the answer is no. I don't actually remember what the next smallest one is. But I will tell you this, it used to be an open question as to whether or not there were infinitely many, and that was resolved only, I'm going to say, about 15 years ago. It is proved now that there are infinitely many Carmichael numbers. As it turns out, they work like primes in this sense, but they are actually rarer than primes. We now know that there's infinitely many of them, but the density of them, I think I've mentioned to you guys before, something about how many primes there are less than the number n. In the same way, you can count how many Carmichaels there are less than n, and it turns out it's a much smaller number. So, no, in fact, what you will discover in the process of me making this proof, you'll start to get a sense of kind of what are the features that you need out of a Carmichael number in order to be a Carmichael number. What is there about these three primes that allows you to kind of pair them together and expect it to be a Carmichael number? So it's a subtle kind of relationship. So that's why it was hard to prove that there's a lot of these. But anyway, so let's work on this. How do I know, for example, that if n is equal to 2, how do I know that 2 to the 561st power is congruent to 2 modulo 561? Well, I could, of course, just compute this. This would be a very large number. It would have, I don't know, about 180 digits. A faster thing to do would be I could multiply 2 by itself 561 times modulo 561, so I wouldn't have any big integers to play with. So we discussed that a little bit last time. A little more rapidly, I did point out to you guys how you could get this with many fewer than 561 multiplications by using that trick of expressing this number in binary. I showed you some calculations. Unfortunately, I can't bring those calculations up again today because my link to the university computer has failed for some reason. But I can prove this calculation. In fact, I'll do it for any n with the same idea without actually doing any extended multiplications. What I do need to use is a prior knowledge of exactly how the number 561 factors into primes. Because we know that to say that these two things are congruent mod 561 means that the difference is a multiple of 561. It's divisible by 561. And that will happen if and only if it is a multiple of each of these three primes. Because since those are distinct primes, this number will be a multiple of their product if and only if it's a multiple of each one separately. So I can check to see whether or not these two things are congruent by mod 561 by seeing whether they're congruent mod 3 and mod 11 and mod 17. So what do I know about 2 to the 561st power modulo 3? Well, that feels like a big number, but when you're working mod 3, there's only 3 possibilities. It's either congruent to 0, 1, or 2. One of these can be ruled out right away. How do I know that 2 to the 561 is not congruent to 0 mod 3?
It's -1 to the power of 561.
Oh, yes. Okay. Actually, you're going in a different direction. That's going to help us decide which of these two is the right one. I'll come to his comment in a second. You know that it's not congruent to 0 because being congruent to 0 means that you are a multiple of this modulus, which is prime, and a power of 1 prime is never a multiple of another prime. So this is actually the unique factorization theorem, the fundamental theorem of arithmetic, coming into play to rule out that one. There are 2 other possibilities, and I was going to have to work a little harder to figure out which one of these 2 it is. But yes, we did just get the hint. When you're working modulo 3, 2 is congruent to -1. And so 2 to the 561 is congruent to -1 to the 561. And you know that when you raise a negative number to an odd exponent, you get a negative number. So of these 3 possibilities, we see that 2 to the 561 is congruent to 2 modulo 3. In other words, I have checked at least this first one is true. Now I can do similar things for 11 and 17, but that gets harder. What am I going to do to see whether or not 2 to the 561st power is congruent to, is it congruent to 2 modulo 11? Well, you could start to work out the pattern for what the powers of 2 look like. You wouldn't have to do 561 multiplications as soon as you establish the pattern. The powers of 2, when you reduce mod 11, it doesn't go on that long. 2 to the 0 power is 1, 2 to the 1st power, 2 to the 2nd, 2 to the 3rd. Now 2 to the 4th is 16, which is a 5. And then after that comes 2 to the, whatever it was, the 3rd, 4th, 2 to the 5th is now going to be twice 5, which is 10, but mod 11, that's the same as -1. And at this point, any further multiplications by 2 will just put negative signs in front of the other numbers that I've already computed. Until you come back to a +1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 to the 10th power is congruent to 1 again, same as 2 to the 0th power. And so every time I go through 10 multiples, 10 powers of 2, I'll come back through to this 1 again. So here's 2 to the 0 power, 2 to the 10th. 2 to the 20th will also be a 1, 2 to the 30th, 40th, 50th, and so on, up to 2 to the 560th power will be congruent to 1. Adding 1 more power of 2 will give me something congruent to 2 modulo 11. So again, we have the congruence that we need. 2 to the working mod 17 works in a similar way. It's a little bit faster. This I should have said these are the congruence classes modulo 11. If you work modulo 17, it's the same principle, but it works actually a little faster because 17 is 1 more than a power of 2. So as soon as you get here, the very next term is 16, which modulo 17 is already a -1, and then doubling it again and again and again and again. Now we've come back to the starting point, and this is only after 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the 8th power is already congruent to 1 modulo 17, which in turn means 2 to the 16th and 2 to the 24th, and in fact, any multiple of 8, 2 to the 8K power, those will all be congruent to 1. At this point, we start to realize how this proof is really going to work. We're messing around with just a base of 2, but look, this principle is going to work in general. If you think about how many times you're going to have to go through the cycle mod 17, you realize it's every multiple of 8 in the exponent gets you back to a 1. So how many multiples of 8 are there? Oh, look, I'm using the division algorithm. And I realize that 561 is exactly 70 cycles of 8, with 1 left over. So 2 to the 560th power will be 2 to that exponent, which is now going to be 2 to the 8th to the 70th times 2 to the 1st. And since we've already decided 2 to the 8th is congruent to 1, the whole mess just turns out to be congruent to 2 modulo 17. All right, we're almost done with this base of 2 because we've decided that 2 to the n is congruent to 2 modulo 3, modulo 11, and modulo 17, which means that this big integer here is divisible by all 3 of those primes, and therefore, since the primes are distinct, 2 to the 561 minus 2 is a multiple of 561. Unfortunately, I didn't just say this when n was equal to 2. I made the claim that this is going to be true for any integer that was coprimed to 561. So can we use the same ideas without having to go through so many calculations with other bases n? And the answer is yes, and you start to realize here exactly what's making it work. I mean, why exactly did it take me 10 powers of 2 to get back to something congruent to 1 modulo 11? Why is 2 to the 10th congruent to 1 modulo 11? That's exactly the Fermat theorem. The Fermat's little theorem implies that 2 to the 10th, well, let me write it, that's 11 minus 1. 2 to the 10th would be congruent to 1 modulo 11, simply because, what was the only condition there? All you needed to know was that the prime 11 does not divide the base 2 that I'm using. So there's nothing special about the 2 here. In fact, the Fermat theorem implies that n to the 10th power is congruent to 1 mod 11 for any integer n that's not a multiple of 11. And then that idea of working through the cycles of length 10, just as we did it for the first 10 powers of 2, it's going to work equally well for the first 10 powers of any integer n. Here, I'll use the same kind of notation that I did in the previous example. So since 561 can be written as 56 times 10 plus 1, that's the division algorithm, it follows that n to the 561st power will be equal to n to the 10th to the 56th times n, which is congruent to 1 to the 56th times n, and that's n. And the only condition that I need is right at this moment, for n to the 10th to be congruent to 1, I do need to know that 11 does not divide n. So the key to making this work mod 11 turned out to be the Fermat theorem. And then if we try that using that same theorem for the other primes, we'll get, again, the same conclusion. So let's just check that. We also know that n to the 16th power is congruent to 1 modulo 17.
Adjust the paper so that it fits within the camera, because I can't see the whole right side of the paper.
Oh, you are right. Thank you for saying something. I've drifted since my early class, I guess. My camera drifts.
Could I see the top paper again?
Let's bring that back. Yeah, there we go.
Okay, thank you.
Yep, I'm glad you asked. Hey, so by the way, I'm putting these recorded things up on YouTube. I don't know if anyone has gone there to check to see if you can download it or stream it. But all this stuff should be there for you to check later. And now that you have told me to get the thing within the field of view of the camera, it should all be visible later. Okay, so again, the Fermat theorem says that as long as 17 does not divide n, then we have this congruence, which has the consequence that, let's see, I have to use the division algorithm here as well. 561 is, I came out to 35/16 when I did the arithmetic before class. 35/16 plus 1. And so therefore, taking n to the 561st power is the same as n to this way of writing things. That's n to the 16th to the 35th power times n to the first. The n to the 16th is congruent to 1, and then there's the n left over. So you can see there's nothing special about the 35. We just end up throwing that piece away. But the key thing is that this number 561 is one more than a multiple of 16, just as it was also one more than a multiple of 10. And it's clearly one more than a multiple of 2 as well. And those numbers 16 and 10 and 2, those are exactly the numbers that are 1 less than the 3 primes involved, the 3 and the 11 and the 17. So let me just finish writing this out. N to the 561 is the same as n to the, that's 2 times 280 plus 1. And in the same way, this will be congruent to 1 to the 280th power times n modulo 3 if 3 does not divide n. So it's congruent to n. So here you go. N to the 561 is congruent to n mod 3. It's congruent to n mod 17. And over here, it's congruent to n modulo 11. I didn't write that in, sorry, mod 11. This condition requires that 11 not divide n. I need 17 not to divide n, and I need 3 not to divide n. But saying that n is not divisible by any of those 3 primes is exactly the same as saying that if n is co-prime to the number 561, then n to the 561st power will be congruent to n modulo 561. And that completes the proof, and it gives us a chance to see exactly what it was that made 561 work. The feature was that, shall I just say, as a corollary to the theorem, this is also true for the number c equals p times q times r if, well, what did we need? I needed p, q, and r to be 3 primes. And then for each one of the primes separately, what I had to know was that if you use the division algorithm on 561, that 561 turns out to be 1 more than a multiple of the number that's 1 less than the prime in question. So 561 needs to be congruent to 1 modulo p minus 1, q minus 1, and r minus 1. And of course, saying that these 2 numbers are congruent modulo something is to say that that something has to divide not 560. It's just the p times q times r. P times q times r is the thing that needs to be congruent to 1 modulo p minus 1, q minus 1, and r minus 1. So it's a funny kind of a condition. When you try looking for sets of 3 primes, you need to know that if you reduce this thing modulo each one of those, now these numbers are not prime, these are composite numbers, but when you do this reduction, you're supposed to get something congruent to 1. You could write this a little bit. Obviously, one thing that's true is that p is congruent to 1 modulo p minus 1, right? P minus 1 is a multiple of p minus 1. So with this piece of information, you'll now know that PQR is congruent to 1 mod p minus 1, if and only if q times r is congruent to 1 modulo p minus 1. So the 3 conditions on these 3 primes about how something should be congruent to 1 modulo each of those 3 moduli, you can say them in a slightly different way if you like. It's saying that each time you take one of the primes, the product of the other 2 primes, or the other 2 primes need to be inverses of each other, modulo this number that's 1 less than the first prime. So, as you can see from this little description, looking for Carmichael numbers that are products of 3 distinct primes it's easy enough to check that you've got them when you've got them, but trying to hunt for combinations of the 3 primes that are magically going to make these things work, that's kind of tricky. That's why it turned out to be so difficult to prove that there would be infinitely many Carmichael numbers. And by the way, this observation was just building on the proof that I had above. You could try a similar kind of description of when you might have a Carmichael number that's the product of more distinct primes. And you can even try to see what would happen if the prime factorization involved different exponents. But it gets to be kind of tricky to describe exactly what the conditions would be on whether or not such a number really meets the definition of a Carmichael number. But the number 561 is fun for that purpose. It manages to pretend to be a prime. So it's an example of what's called a pseudo prime. Carmichael numbers are also called pseudo primes, precisely because they seem to be following the condition of the Fermat theorem, even though they're not really primes. A number is called a pseudo prime if it manages to make this kind of a condition true for a single value of n. Typically when n is 2, people try this test. And I did some calculations with you last time on my computer to show that you could easily show that certain numbers are not prime just with a single one of these tests. But you do have to watch out for the pseudo primes that, like the number 341 I mentioned last time. It's a mod 2 or a base 2 pseudo prime. The Carmichael numbers are the ones that are trickier though, because they manage to look like a prime no matter what base you use, as long as you choose a base that doesn't have any factors in common with C. All right, I am making up a homework set for you guys where I'm going to ask you to try some calculations of these types to see if you can use the Fermat theorem to decide whether or not certain numbers are primes, or to do some reductions of numbers, expressions that seem to have high exponents in them, to see if you can figure out what they would be congruent to some modulo some much lower numbers. Just to kind of force you to get used to the statements of the Fermat theorem. I'd like to show you one example. Here's an interesting theorem. If P and Q are 2 distinct primes, different.
May I interrupt for a question?
Yes, certainly.
For the last corollary, did we say that all numbers C that satisfy the corollary are the Carmichael numbers, or it's the other way around? All the Carmichael numbers satisfy the corollary?
No, it's the first one. You're talking about this statement here?
Yep. That part.
Yeah, this is, maybe if I put the word if in there, would that help? If you know that a number C is the product of 3 primes, then it will be a Carmichael number if this condition is true. So this is a way of constructing some Carmichael numbers. It doesn't, there's no guarantee that they don't necessarily have to have that form.
Okay, now it's clear. Thank you. And I think there's a question in the chat for Carmichael numbers.
Oh, thank you. I can't always monitor the chat. Thanks for bringing that to my attention here. Does it need to be 2 to the 5 or 6 power congruent to 0, 1, 2, 3? Okay, no. Okay. What is the use of Carmichael numbers? No, the use of them is primarily because people need to have tests for primality. So let me put this into context for you. As a practical matter, people actually do care about whether a number is prime or not, because they need to use primes in certain kinds of calculations. For example, the cryptography calculations, where the theorem, the recipe, the procedure all says, start with a number which is known to be prime, and then do the following calculations. And that's fine, because we know that if you wanted to make some sort of a secret code that was based on you having a prime that was special to you, your secret decoder ring is a prime, okay, everybody can have their own secret prime because we do have a theorem that there's infinitely many primes. Great. But just knowing that there's infinitely many primes doesn't necessarily tell you how to find a number that's prime. So you guys all know about the kind of naive way of deciding whether a number is prime or not. Just try dividing it by 2 and 3 and 4 and 5 and see if it has any divisors. But if you have a number that's as big as your Social Security number, that's already difficult. And if you have a number that's 100 digits long, well, that would require, 10 to the 100th power possible divisions, and there's not enough time in the life of the universe to do that. So people would like to have a test that tells them whether or not a number is prime. And the way that this is usually done is by just using this converse to the Fermat theorem. Everybody wants to just do this. They write down a very big integer and they say, I think it might be prime. I don't know, let me check this. I'll put in n equals 2 and see if I get 2 to the pth power congruent to 2 mod p. Now that's not as hard a computational task as you might think. I showed you guys last time how you could calculate this left-hand side pretty quickly by using the binary decomposition of that number p. Even if a p is a 100-digit number, when you express it in binary, that's a few hundred bits. So this left-hand side could be computed with a few hundred multiplications. That takes a computer just a fraction of a second. And if you compute n to the pth power and you don't get a number n, the same number n that you started with, well, then your number p isn't prime. So people like to use this so that they can manufacture big primes. They basically just pick a number at random and look to see if it's prime. And if it's not prime, they go on and they pick a different number n. The concern then is, what if you have taken a big number n and you compute n to the pth power and it does come out to be congruent to n? Well, that doesn't really mean that the number n is prime, as this example shows. But even in this example, what you learn is, okay, if you have a number n which has managed to make 2 to the pth power be congruent to 2, then try 3 to the pth power or 4 to the pth. Try some other base and see if you can get it to be prime. Because in practice, people say, oh, it basically never happens that you can raise every single integer to the pth power and expect to get that integer out, except when you have a prime modulus. That's when people stumbled on the Carmichael numbers. Oops, where'd they go? Here. The Carmichael numbers are exactly the numbers that are going to pretend to be prime, even though they aren't, by using this test. They will manage to, there'll be a false positive, if I can put it that way. They're a false positive for this primality test. So it's not so much having particular Carmichael numbers that bother us or excite us, but it's the fact that they exist that puts a wrinkle into this process of deciding that a number is prime, and therefore makes it difficult to make a big number prime. So that's why people study them, is they kind of wanted to know, maybe there was just a finite number of Carmichael numbers, so we could just make a list of them, and then in our algorithms for testing whether a number is prime or not, we just first make sure it's not a Carmichael number, and then then we go and do the rest of the Fermat test. But the fact that there's infinitely many Carmichael numbers, that kind of puts the kibosh on that plan. So in fact, I'll tell you what people do in those procedures that require having a large prime number is they run a test, and if the number passes the Fermat test for a few different bases, then they pronounce the number to be probably prime, and they leave it at that. And everyone has to acknowledge that, yes, there are Carmichael numbers that are not prime, even though they pass this kind of a primality test. So it's a weird kind of a language, because a number either is prime or it's not, but we call it probably prime just because we can't quite decide what it is. I'll tell you guys too, I was very disappointed when I first learned about these algorithms, because I thought there must be some very cool methods that people have for creating large primes. I don't know if you guys have heard these stories, but there's the so-called Mersenne primes, where you look at a number that's 1 less than a power of 2, or the Fermat primes that are 1 more than a power of 2. And there's a lot of primes of this type. There's not so many primes of this type, but I thought people had a cool way to make big primes. And as it turned out, they don't. All they do is they pick a number at random, and if it's not prime, they pick another number at random. And they just keep picking numbers at random until they stumble on a prime, using the fact that actually primes are not all that rare. They sooner or later know that they're going to find one. So it's a little bit disappointing, but yeah, it works. All right, let me give a quick theorem here. This one I don't actually have an application for, but it is cool to see it. If you take 2 different primes, then I'm going to write a funny number on this side of a congruence, and I know what it's congruent to on the other side. Oops, sorry, p minus 1. This will always be congruent to 1 modulo p times q. Proof? Well, all the coolest theorems seem to have a prime modulus, and this one doesn't. But the way we prove this is the same way we did the previous theorem. 2 numbers are congruent to each other modulo p times q, if and only if they're congruent to each other modulo p and modulo q. So let's do each of those separately. Working modulo p, obviously p to the q minus 1 power is going to be congruent to 0. That's a high power of p itself. On the other hand, that expression, well, now if p and q are distinct primes, then in particular q is not a multiple of p, which means that I can use the Fermat theorem, and I know that that one is congruent to 1. And now, if you add these 2 things together, you have 0 plus 1, and that gives you 1. It's not just congruent to 1, it's equal to 1. And similarly, mod q, we discovered the congruences go the other way around. This time p, that should have been a minus. P to the q minus 1 is congruent to 1, and q to the p minus 1 is congruent to 0. So again, when you add the 2 terms together, this time you've got a 1 plus 0, and that's a 1 again. So the left-hand side and the right-hand side differ by a multiple of p, and they differ by a multiple of q, and so therefore they differ by a multiple of p times q, and that's your theorem. Cute, huh? All right. I have another theorem which in principle could be a perfect primality test. The Fermat test has the defect of the Carmichael numbers. They slip by, they make you think they're prime, but they're not. Here's a theorem that doesn't have that defect, but unfortunately has other defects. So the theorem is due to Wilson, who's a person that I don't really know anything else about, because as far as I know, he's only got 1 theorem. And this theorem says if n is a prime number, then n minus 1 factorial will be congruent to -1 modulo n. If n is a composite number, then n minus 1 factorial is congruent to 0 modulo n, with one exception, 4 minus 1 factorial, that's 3 factorial, which is 6, and that's congruent to 2 modulo 4. So, if you want to know whether a number is prime or not, compute this factorial and reduce it modulo n. You will only get one of 3 different answers, and 2 of those answers signal a composite number, and the other answer signals a prime number. So it's a perfect primality test, except for one thing. Unless the CIA is hiding some secret from me, nobody knows a good, quick way to compute the factorial of a gigantic number n. Even if you only have to do the computations modulo n, there doesn't seem to be a fast way to do this computation. So, okay, maybe it's not entirely a practical theorem, but it's a cool theorem, and what's even cooler is the proof. This is a proof that, a technique of proof that turns out to be useful in some other circumstances too. The proof consists of trying to calculate exactly how would you calculate n minus 1 factorial. By definition, this means the product of all the numbers from 1 up to n minus 1 inclusive. Now, any normal person would proceed to calculate this by first multiplying these two numbers together, and then those next number, and then the next and the next. So you'd have a sequence of numbers. You could reduce all of the calculations mod n as you go, but nothing interesting would materialize until the very end, and you would see that you get something congruent to -1. But we can be more clever about this. What we should do is we should say that collectively, what you see here are all of the non-zero residue classes modulo n. I mean, when you use the division algorithm, every number is congruent to exactly one of these things mod n, except for the multiples of n. They would be congruent to 0. So using the notation that we had before the break, these would be all of the elements of z mod n except for 0. Now, watch what happens in the case where n is a prime number. If n is prime, then one of the things we've decided is that, okay, well, no matter what n is, if you take an integer mod n, take an integer which is co-prime to n, then it'll have an inverse mod n, a unique inverse mod n. And when n is prime, the things that are co-prime to n are, well, all of these things. They're all co-prime to n. So when n is a prime number, every one of these has an inverse mod n. If you take any integer mod 11, from any of the integers from 1 to 10, it'll have an inverse mod 11. And there'll be a unique inverse. There'll be exactly one other thing that you can multiply a 3 by to get something that's congruent to 1 mod 11. And that one thing happens to be 4 in this case. If you turn around and you ask 4 for its inverse, of course, then the inverse of the inverse is the original one. So 3 and 4 are paired off. They are inverses of each other, mod 11. And staying with mod 11, 2 and 6 get paired off. And then I guess it's 5 and, oh wait, what are the pairs here? Mod 11, the inverses are 2 goes with 6, 3 goes with 4. Who's left? 5 goes with 9. I got 2, 4, 5, 6, 7 must go with 8. And, oh, I skipped 1, 2, 3, 4, 5, 6, 7, 8, 9, oh, and 10. So here's all of the 10 residue classes mod 11 listed out, but I've listed them now in pairs. So as you want to compute 10 factorial, you need to multiply these 10 congruence classes mod 11. Don't do it this way. Do it this way. Be clever about it. You multiply 1 times 2 times 6 times 3 times 4, and the other pair, and the other pair, and the 10. And every one of these pairs multiplies out to be congruent to 1 mod 11. And in fact, this works modulo any prime. Near mod any prime, we have every non-zero residue class mod n has an inverse. And when I multiply all these numbers together, I'm multiplying them in pairs to get a bunch of 1s, with 2 exceptions. These 2 numbers don't show up in a pair because they are their own inverse. 1 inverse is equal to 1, and 10 inverse is equal to 10, right? 10 times 10 is 100, which mod 11, that's congruent to 1. How often does that happen? Well, x can only be the inverse of x if x squared is congruent to 1. And that means that x squared minus 1 is supposed to be a multiple of this prime n. X squared minus 1 is x minus 1 times x plus 1. And if n is prime, that happens if and only if n divides one of those 2 factors. And that means that x is congruent to either 1 or minus 1 mod n. This is the key thing that makes primes different from other moduli. When you look for a square root of 1, there are only 2 square roots of 1. That's 1 and negative 1. So in this pairing process, everything gets paired with something that's different from it, except for 1 and negative 1. And so as a conclusion, n minus 1 factorial will be congruent to 1 times a bunch of pairs of something in their inverses. And finally, at the end of the list is the number minus 1, or n minus 1 itself. And when you multiply all this out, you get a minus 1. So that gives us the proof in the case where n is prime. That's the hard part. Obviously, this one is a simple calculation. In the case where n is a composite, as soon as you know that a number is a composite, that means it can be written as a product of 2 numbers that are both less than n. And when you compute n minus 1 factorial in that case, like to compute 11 factorial mod 12, that's when you can multiply it out in this way. If you compute 11 factorial, somewhere along the way, you'll have the 3 and the 4 multiplied together, which will give you something congruent to 0 mod n. So these 2 parts of the proof are trivial. This is the part that's got this really cool proof. All right, you guys are pretty quiet today. Comments or questions on this? Okay, I'm trying very hard to watch the clock so I can see that I have actually only gone 1 minute over. I want some credit for only going 1 minute over today.
Yeah, way to go.
Thanks. So I'm going to stop today, and I will put questions about that use both Wilson's theorem and the Fermat theorem into the homework for you. I should have that done by later today.
Could you show the second sheet?
The end of the proof here for Wilson's theorem. It's I didn't write it out in full sentences. I guess I was speaking as I wrote, so there's not a lot to see here. But the key idea is that the terms in the factorial are lots of products which are taken in pairs, and all the pairs multiply out to be a 1, except for the 2 things the 2 things that are their own inverses, and that's just the 1 and the minus 1, and that's why minus 1 is the product.
Thank you.
Okay, guys, thanks for showing up. And I'll see you in 48 hours.
Have a nice day. See you on Friday.
Thank you, you too.